happen to be. This is Neil Paulhemus. I will be doing the webinar this morning, and I'm quite encouraged that quite a number of people have pre-registered for this webinar. It's going to be the first in what will be our fall-winter series on various statistical topics and how to analyze different types of data using Statgraphics and Criterion. Today's topic is time series analysis, which is basically the analysis of sequential data collected over time. It's a topic actually that's quite of a lot of interest to me, and has been actually since I was a graduate student many years ago, when I had the chance to take a number of courses from some folks who knew quite a bit about time series analysis. I had the chance to take a basic course in time series modeling from Stu Hunter, who worked with George Box closely on the development of ARIMA models. Took a course from a fellow named Peter Bloomfield, who was very much into the use of Fourier analysis, periodograms, and so forth to find periodicities, cyclical effects in time series data. And also I had a chance to take a course in basic exploratory data analysis from John Tukey, and part of what John talked about in that course were his nonlinear smoothers, and I'll be showing some of that today as we go through Statgraphics. Now, I want to invite you all, as I have in the past, to send us any questions via the GoToWebinar screen. We'll be monitoring any questions that you submit by sending us messages, and then at the end of the webinar, I'll go through as many of those as I can. And actually, I'll stay, hopefully, as long as necessary to answer any of those questions. We've also posted on our website, on the link for the webinar this morning, the slides that I'll be using. My webinar here will actually be a combination of some PowerPoint slides and some live use of Statgraphics. We posted, though, the slides on our webinar page, and also the sample data sets that I'll be talking about. You can go ahead and download those at your leisure and hopefully try out some of the techniques that I'll be showing you today. Okay, now the procedures I'll be talking about in this webinar are under the time series and forecasting sections on the Statgraphics Criterion menu. There are 4 or 5 main procedures in Statgraphics that are designed to handle time series data. There's a procedure called Descriptive Methods that creates various types of plots, time sequence plots for the data. It also creates autocorrelation functions, partial autocorrelation functions, periodograms, all of which I'll talk about in some detail a little bit later in the webinar. There's a procedure in Statgraphics for smoothing time series data that contains both linear and nonlinear smooths. There's a procedure for doing a seasonal decomposition and seasonal adjustment of time series that fluctuate over some fixed cycle. And finally, there are a number of procedures for doing forecasting. Actually, 2 primary procedures for forecasting time series data. One called user-specified models, where you tell it exactly what type of forecasting model you want to use, and then it goes ahead and estimates any unknown parameters in that model. There's also, though, an automatic model selection procedure that will fit a whole bunch of models and pick out what appears to be the best model, at least the best in terms of its ability to forecast the historical data. Now, we should probably start by talking about what we mean by a time series. Basically, a time series is a set of sequentially ordered observations. data recorded, for example, once a day, once a month, every 10 seconds. The important features of that, though, is the fact that it has a specific order. The standard notation for time series, at least that I'll be using in this webinar, I'll express the observation at time t as y sub t, where t will range over the integers 1, 2, 3, and so forth up to n being the number of observations available in the time series. The primary complication that makes time series analysis different than a lot of other standard statistical analyses that you're used to is that the observations are usually not independent. Observations close together in time instead tend to be related to each other. The word we actually use for that is autocorrelated. And autocorrelation exists when a variable is correlated with itself, hence autocorrelation with itself at different points in time. And I'll be talking about autocorrelation functions and things like that as we go through the webinar here. Now, I've pulled up a couple interesting data sets, at least they're interesting to me. The first data set we're going to be looking at is actually the U.S. unemployment rate. It turned out that just back last Friday, the government reported the latest figures on unemployment. Now, the unemployment rate is defined as the percentage of the civilian labor force, civilian doesn't count the military, defined as the percentage of the civilian labor force that are actively looking for a job but can't find one. Now, there's a lot of controversy over that particular definition because, for one thing, it doesn't count people who have given up looking for a job. People who found it so hard to find a job that they gave up are actually not considered part of the labor force. Be that as it may, it's a statistic that a lot of people look at because it does obviously measure, at least in some sense, the health of the economy. Now, I found the data actually on a website, very interesting website, www.bls.gov, BLS being Bureau of Labor Statistics. There are a lot of interesting time series on that particular website. I pulled down the data, actually, the unemployment rates between January 2001 and the latest figure, which was November 2011. Now, there are two different numbers that you can pull down from the Bureau of Labor Statistics. One is the unadjusted rate. Okay, that's the actual, at least estimated unemployment rate in November, which turned out to have been 8.2%. And then there's something called the seasonally adjusted rate, which is the one that's normally reported. That was 8.6%. The difference between unadjusted and adjusted rates has to do with whether or not they've compensated for the natural seasonal effects that are present in a lot of time series, particularly economic time series. In fact, unemployment in November tends to be a little lower than average every year just because a lot of people are hired on a temporary basis to help out during the holidays. So the fact that it was 8.2%, if you tried to compare that, for example, with June and some of the summer months where the unemployment is high, it wouldn't be fair. So they do a seasonal adjustment to take out the seasonal effects. And I'll be showing you how Statgraphics can actually do that seasonal adjustment. What we have, though, here then will be two time series, an adjusted rate and an unadjusted rate. Now, at this point, I think what I'll do is I'll go over to Statgraphics, and I'll be running the latest build of Statgraphics Centurion. This is version 16.1. And I'll start actually by opening up some data sets. The data set I want to open up here is actually a data set called unemployment rate. And what you can see is that I have a file, and this is one you can download after the webinar, incidentally. It's up on the website. It's data on a monthly basis measuring the unemployment rate in the U.S., both unadjusted and adjusted. Now, I'm a big believer in plotting the data before you do anything else with it. So the first thing I did in the notes, if you download the notes, is you'll see I went to the multiple XY plot procedure. Let's see if I can get there. There it is. Multiple XY plot. And decided to plot both the unadjusted and adjusted data by month. Okay, well that would bring up a plot, and on this particular plot, let me pull the labels up here, you've got the unadjusted rate plotted using little blue squares, and the adjusted, seasonally adjusted rate using red circles. You notice a number of things. You notice that unemployment has changed quite a bit since January of 2001. In fact, it was down around 4% at the beginning of 2001. It went up to a little over 6% at the beginning of 2003, then came back down to around 4.5% in the beginning of 2007. And then at the beginning of 2009, or I guess it was 2008, no, that's 2009, started to rise quite precipitously. Actually went over 10% at the beginning of 2010 and has been coming down at a rather slow pace since then. Now, there are a number of interesting things to do with this series. It's interesting to try to estimate some of the important components of this time series. It also can be quite interesting to try to forecast what's going to happen in the future. And we're going to do both of those over the next few minutes. Okay, now, before we do that, though, let's go back to PowerPoint, and let's talk a little bit about time series in general. The classic model for a time series considers it to consist of 4 different components: trend, cycle, seasonality, and randomness. By trend, we would mean the long-term changes in the underlying process mean. Okay? You know, if you were working with pricing data, consumer price indices, or and such, the long-term trend in prices has always been up. Maybe not over the last couple of years, but the long-term trend at least has been up. Around the long-term trend, one tends to see cyclical variations of 2 different sorts. There are things like the business cycle that is a cyclical variation around the mean but doesn't have any particular fixed period. And that's usually called cycle, business cycle. There are also seasonal effects, which are cyclical variations around the mean but having a particular fixed period. The unemployment rate has definite seasonality. As we'll see, unemployment is high at the beginning of the year and during the summer months, and relatively low in the spring and the fall. And then finally, there's randomness, which is all the everything else. It's the random fluctuations around the trend, the cycle, and the seasonality. When we model time series, we have typically a choice of using either a multiplicative model, where the 4 components are assumed to multiply each other, or an additive model where it's assumed that the different components add to give the result. When you're working with economic data, things tend to be multiplicative in nature. Changes tend to be proportional, and therefore, by default, we'll often be using, and we will be using today, primarily a multiplicative model. I also made a note on the slide that if you have data which is multiplicative but wish to use an additive model, taking logs will always change a multiplicative model into an additive model. Now, keep this model in mind where the data is represented as trend, cycle, seasonality, and randomness. And let's talk about some of the smoothers that are available in Statgraphics. Statgraphics has a special procedure for smoothing time series data. And it provides two basic types of smoothers. There are linear smoothers and nonlinear smoothers. Linear smoothers are weighted moving averages designed to smooth out the randomness and also, if you pick the right moving average, eliminate the seasonal components so that you can see the underlying trend cycle. And in just a moment, we'll go ahead and put a moving average through our unemployment data, and you'll see that it does a pretty good job of showing us the underlying change in the level of the series. Statgraphics, though, also has a number of different nonlinear smoothers that John Tukey developed, which are variations on running medians. They're based on running medians rather than moving averages. And they're basically designed to reduce the impact of outliers. Okay, one of the things you'd like to do typically when you're smoothing data is to have the outliers not have too much impact on the results. Okay, now I'm going to show you both of these types of smoothers. So I'm going to start actually with the linear smoothers. Linear smoothers are basically weighted moving averages of the data and the data in some window of time. So for example, if I wanted to estimate a smooth value at time t, I may take some linear combination of the observation at time t and also the observations perhaps m time periods before t and m time periods after t. That would typically be called a centered moving average. It's centered at time t. Statgraphics offers actually a number of different types of moving averages. We have simple moving averages where the W's are all the same. We also have exponentially weighted moving averages and a number of moving averages that have been developed by actuaries over the years called Spencer's and Henderson's moving averages. Now, to do smoothing in Statgraphics, what I'll go is actually to the Describe menu. If you go to the Describe menu, you'll see a section on time series. And one of the sections on time series is smoothing. Now, this will bring up, as most dialog boxes, procedures, menu items in Statgraphics do, a data input dialog box. Now, I'm going to start, in this case, by smoothing the unadjusted unemployment rates. This is the unemployment rate without the seasonal adjustment. So I'll pick that particular column and put it in where it says data. As far as the next field, which is time indices, I actually have two choices. I can either put in the name of a column that identifies when each of the observations was recorded, or instead of that, if I didn't put anything there, I could go down here, for example, and click and tell it instead that my sampling interval was once a month, once every month, starting at January 01. Okay, you have a choice. If you don't put anything up in the field here for months, it'll go down to where you say sampling intervals and actually generate something to plot against for you. Okay. If the data were seasonal, I could type in a number like 12, which would indicate to the process that I expect the data to follow a cycle with a period of 12, in this case 12 months, or not, as I like. The time series procedures also have a trading days adjustment field. If you're taking, for example, sales data, monthly sales data, you might like to adjust the data for the fact that some months have more business days or more trading days than others. You know, some months of the year may have, I don't know, what is it, about 20 business days. Sometimes it could be 21, other times 19. If you want, you can create another column that has the number of trading days associated with each row of your data file, and Statgraphics will do an adjustment to basically compensate for the different number of trading days in each of the rows of the file. That's irrelevant here. I'm looking at unemployment rates, but there are times when you might like to do that. Okay. So I'm basically going to tell it to take the unadjusted employment rate and plot it versus month. Now, the next thing it's going to do is it's going to offer me different types of smoothers. And in fact, I can apply in sequence up to 2 different smoothers. You need to specify typically at least one smoother, but if you like, after doing this first smoother, you can smooth the smooth with the second smoother. Now, the first several choices are the moving averages, the Spencers, the Hendersons, the EWMA, which are the linear smoothers. And then things like 3R, SS, 3R, SSH, and so forth are Tukey's nonlinear smoothers. Now, for this data, since it is monthly, it's a good idea to start with a moving average of 12. If you do a moving average of 12, that means you'll be smoothing 12 consecutive observations. And that will, for example, contain 1 January, 1 February, 1 March, and so forth. That should remove the seasonal effect because it'll have one of each month in it at the same time that it's dampening down the random effect. So let's go ahead and press OK. And then, as usual, we'll offer different tables and different graphs. Let's just press OK again. And here you can see what happens when we apply that particular smoother to the unemployment rate. We actually get a pretty good smooth estimate of what was happening, the underlying trend cycle in the data. Okay, now that's a linear smooth. As I said, Statgraphics also provides a number of non-linear smoothers. These were developed by John Tukey and are typically based on running medians of either 3 observations or 5 observations. You know, instead of taking a moving average, you take a moving median. Now, Tukey had a whole special notation for describing his nonlinear smoothers. A typical smoother, widely used smoother, is something that Tukey called the 3RSSH smoother. The 3 means we'll start by smoothing the data with a running median of 3. So we'll basically take the first 3 observations, find the median. Observations 2, 3, 4, find their median, and so forth, and smooth out the data with a running median. The R means repeat that running median again and again until nothing changes. So basically, you smooth the data with a running median of 3, then you smooth the smooth values with a running median of 3, and you do it over and over and over again until there's no change. Unfortunately, because of the nature of the median, that tends to give you not the smoothest result. In fact, you end up with things called mesas and dales, which are little flat periods because of the nature of the median. A mesa is sort of a flat peak, and a dale is a flat valley. So Tukey developed something called a splitting mechanism, where you make a little adjustment to the points where you see mesas and dales, and then you repeat the 3R operation. In fact, 3RSS means do a running median of 3, repeat it till there's no changes. Do the smoothing operations and repeat the 3R. The splitting operation and do a 3R. Then split it again and do a 3R. So it's a whole sequence of 3R smoothers. And then at the very end, you'll see that there's an H. H means that what we'll do at the very end after having done all this is do something called Hanning. Hanning proposed that when you were all done doing the nonlinear smooth, you apply as a final smooth a very simple moving average, a 1/4, 1/2, 1/4 moving average, in order to give it even a smoother appearance. Now, I'll show you how it works in Statgraphics. Let's take this particular data and go back by pressing the right mouse button and saying Analysis Options, and ask for one of two key smoothers instead, for example, the 3R SSH. What that'll do is give you the result you're seeing on the screen right now. Basically, a running median of 3 is going to resist an isolated outlier. Because if you're taking running medians of 3 points, and 2 points are close together and 1 point's way away, well, the median is going to be one of the points that are close together. So it gives you a resistant smooth, a smooth that resists outliers. Now, it's not all that obvious here because there aren't any big outliers, but let's suppose I had a point here like row 109, and let's suppose there was a big outlier there. Let me actually go back to the data to that point and type in for the moment, instead of 10.6, type in a 15. And then I'll click back here to the smooth. Okay, I just temporarily put in an outlier there. And you can see that this particular smooth pretty much ignored that outlier. Single isolated outliers are ignored by running medians of 3. If there were 2 outliers in a row, you'd probably want to use a running median of 5 because that'll ignore a pair of outliers. Anyway, those are nonlinear smooths, and they're really good for removing isolated outliers. The first time I ran into those, incidentally, was, again, back as a graduate student at Princeton when I was studying with Stu Hunter. He had a contract with the Federal Aviation Administration that had to do with processing radar returns coming into air traffic controllers. And as you can imagine, when radar returns come into air traffic controllers, every once in a while there's a little blip, a little outlier. And you really don't want to have the controller all of a sudden see on his screen an aircraft that moves suddenly to the left or to the right. So radar returns are typically smooth before they're shown to the air traffic controllers, and a nonlinear smooth like this is quite a good way to process that type of data. Anyway, let's go back to the data, and let me put back the 10.6 I had here before, and go back. I really don't want to keep that outlier in the data. Now, you can also do smoothers in sequence. You can see, for example, that this is not as smooth as one of the linear smoothers. So a good thing to do, if I go back here to Analysis Options, is perhaps to start with a nonlinear smooth, which will get rid of the outliers, and follow it with a linear smooth, which will give me a smooth result. So what I'm going to do now is actually do a 3R SSH smooth, and then smooth that smooth with a simple moving average. Okay, that'll end up giving me the best of both worlds. I'll have applied the nonlinear smooth to resist any outliers, and now I'm applying the linear smooth on top of that to give me a nice smooth result. Okay. Well, that's an illustration of what the smoothing procedure in Statgraphics will do. I hope you find that interesting. Let's go back to the PowerPoint slide for a moment and look at another procedure. And the second procedure I want to look at is the seasonal adjustment procedure. Statgraphics does contain a procedure for doing a seasonal decomposition or a seasonal adjustment on a time series. It's designed to remove the seasonal component from a time series, leaving the other components behind. For example, if I have a multiplicative model, if I was able to estimate the seasonal component in the time series, I could then take my original time series, my y sub t, and divide it by the seasonal component at time t, and leave behind the trend, cycle, and randomness. When the Bureau of Labor Statistics seasonally adjusts the unemployment rate, what they're doing is basically taking the data, dividing it by a seasonal index so that you get a consistent view of everything with the seasonality removed. Okay. Now, Statgraphics will do this sort of seasonal adjustment for you. If you go to Describe Time Series Seasonal Decomposition. Now, the seasonal decomposition will run in a very similar way to the smoothing. You put in the time series you want to analyze, the time indices or the sampling interval, and also the seasonality. And on the seasonal decomposition, you do need to specify the seasonality. In this case, I've put in 12, indicating that there are 12 basic seasons, January through December, and I would expect whatever the seasonality is to repeat with a period of 12. If I press OK, the next thing that will pop up is an adjustment options screen. Now, I've been analyzing and will continue to analyze the observations as provided by the Bureau of Labor Statistics. There are times, however, when it can be useful to transform the data, to take a log or a square root or a reciprocal or some power transformation of the data before doing the seasonal adjustment or the smoothers. And all the time series procedures do allow you to make that sort of an adjustment. There's also in our time series procedures an adjustment that you can add based upon inflation. If you were looking at something like the consumer price index or the prices of some commodity, and you believe that there was some relatively constant inflation rate over the period, you could type in an adjustment, type in what you would assume the rate of inflation was, and hopefully it wasn't 1% per month, but if I typed in 1, that would indicate 1% per month, and it would adjust the data before doing whatever analysis it was about to do. Now, I'm not going to do anything like that with the unemployment rate. I'm going to leave that at 0. Okay, let's press OK. And now you can see, again, various tables and graphs. I can get an analysis summary. I can get some seasonal indices. It'll plot for me the trend cycle, the seasonal indices, the irregular component, which would be the random component. It'll plot the seasonally adjusted data. And there are a couple sub-series plots that it will also create. Okay, so I'm going to ask for several of those and press OK. And let's see if I can show you exactly what it's done. The first thing that a seasonal decomposition procedure will do is it'll start and it will smooth the data. Now, by default, what Statgraphics will do is go in and use a simple moving average with a span equal to whatever the seasonality is. So that's just the same smoother I showed you before. It's a smoother with the moving average of 12 applied to it. Okay. Now, what that's going to estimate for me is the trend and cycle. The deviations around the smooth contain at the moment the seasonal effect and also the random effect. The next step in the seasonal decomposition will be to take a particular month like January and calculate the ratio of the Januaries to their moving average. So, for example, take this January, take its ratio to its moving average. another January ratio to moving average, another January ratio to moving average. And for each January, we'll compute the average of the ratios to the moving average. Okay, now Januaries, you'll see in just a moment, tend to be high, so all Januaries will tend to be somewhat above the moving average. And then you do the same thing for February and March and April and so forth, coming up with what then becomes a seasonal index for each month. And if I put this plot back and look at the second plot, let me double click on this, the second plot will actually plot out the seasonal indices. Now, it also will scale the seasonal indices so that an average month would have an index of 100. Januaries, on the other hand, have an index of about 109. That means Januaries tend to be about 9% higher on average than an average month. Unemployment tends to be high in January, February, and March, relatively low in April and May, high again in June and July. August is about average, but then September, October, November, December, they're always relatively low. So you can see, for example, for November, which is what I was worried about here, unemployment tends to be only about 96% of an average month. So to report a seasonally adjusted value for unemployment, I typically take the unadjusted rate, divide by 0.96, which would then give me a seasonally adjusted value. And that's what Statgraphics is going to do. It's going to take each of the points in our data set, divide by the associated index, and come up with an adjusted, a seasonally adjusted value. Now you might notice if I put my mouse down here that my seasonal adjustment of the 8.2 gave me an 8.52 for the seasonally adjusted value. Now the Bureau of Labor Statistics at 8.6. They're actually using a slightly different smoother on their initial step to do a trend and cycle. They're also using more decimal places. So I can't expect to get exactly the result that the Bureau of Labor Statistics does. But that is the procedure that's typically used to do a seasonal adjustment. All right, now there's one other plot that's available when you do a seasonal adjustment, and that is a seasonal subseries plot. This is a real interesting plot that was developed quite a few years ago, which is a different way of looking at seasonal data. It's a plot I happen to like because it can show you a number of different components on a single plot. The way that a seasonal subseries plot works is the following. I start by, let's say, taking every January. I compute the average January and show it as a horizontal line, and then plot vertical lines from each January to their average. So what you see in this little section of the plot is all the Januaries, the first one being quite low and some of the later ones being quite high, plotted against their average. You do the same thing with the Februarys, the Marches, the Aprils, the Mays, and so forth. What you see if you look at the horizontal lines, the red lines, is another picture of the seasonal effects. High at the beginning of the year and the summer, low in the spring and the end of the year. You can also see, though, within each month what the trend looks like. And if you look at the pattern of the lines in each month, you get an idea of whether the trend has been similar in all the months or different. In this particular data, they're quite similar. All the months started low and ended high in this particular data set. Sometimes, though, you'll see significantly more trend in some months than others. So it's a very interesting plot in terms of giving us a picture of a number of different components of the time series in a slightly different way than all the time sequence plots we've been looking at so far. Okay. Well, that was the second procedure I wanted you to see, was the seasonal adjustment procedure. Okay. The third procedure I want to talk about is forecasting. Statgraphics has a number of different procedures designed to help us predict future values of a time series. Now, we have a number of different types of models that we can fit, as you'll see in a few minutes. We've got moving averages, exponential smoothers, trend models, ARIMA models, a number of different types of models. Basically, though, you can look at the models and think of them as being two basic types. We have models that are auto-projective. An auto-projective forecasting model basically forecasts the future based solely on the past behavior of that time series. So, for example, I can just take my unemployment rate series and by looking at how it behaved in the past, forecast what's going to happen in the future. Okay? You can imagine that that can be quite useful, particularly for short-term forecasting, but not very likely to be all that great for long-term forecasting. There are also, though, input-output models. Input-output models would include information from other predictive variables, other time series. And usually what you look for if you're building an input-output model is some sort of a leading indicator, some other time series that moves before the one that you're trying to predict. And if you can find a leading indicator, then you can improve on the forecasts beyond what an auto-projective model would be able to do. Okay, now let me illustrate for you, if I can, oh wait, actually let me show you for a moment first a list of some of the different forecasting methods that we have. We have in our forecasting procedures things called random walks, mean models, trend models of various sorts, S-curves, moving averages, exponential smoothers, and the models popularized by Box and Jenkins called the ARIMA models. At the same time, when you're doing forecasting, you can obviously also make adjustments for either inflation or some mathematical transformations on the data if you like. I'm going to illustrate for you two procedures in Statgraphics. I'm going to illustrate for you a procedure that's under the forecast method. Actually, both of these are under the forecast menu item. The first is called user-specified model. If I select user-specified model, then what it will do is it will fit a particular model that I tell it to fit. For example, if I wanted to do simple exponential smoothing, I might go to the user-specified model and tell it to do simple exponential smoothing. Now, it will, if I ask it to, find the optimal value of any unknown parameters. And if you've done any exponential smoothing, you know it involves an alpha, a smoothing constant. And it will find the optimal value of alpha for me if I ask it to. Okay? But basically, in the user-specified model, I'm telling it what type of model to fit. We also have in Statgraphics an automatic model selection procedure. What that procedure does is it fits a lot of different models and automatically picks the best one. If you like, you can have it fit all the models, and according to a particular optimality criteria, will tell you which one seems to forecast at least the past history of the data the best. Okay, now that's actually where I'm going to start. I'm going to start with the automatic model selection procedure, which you will find in Statgraphics under the forecast menu. Here you'll see those two procedures I just talked about. And if you go to automatic model selection, you can have the procedure fit lots and lots of different models. Now, I'm going to actually have it forecast both the unadjusted and the adjusted unemployment rates. I'll start with the unadjusted rates. So I'll put in the unadjusted rates. I'll tell it that it comes once a month. And I'll also tell it that the seasonality is 12. If I give it a seasonality in that particular field, it'll fit seasonal models. If I don't put anything in that field, it'll only fit non-seasonal models. Now, down here, I'll tell it how many forecasts I want. And in this case, I'll tell it, let's go ahead and forecast the next 12 months. Okay? That will be December of this year through November of next year. Fairly interesting because we do have a presidential election coming up next November. And the state of the economy may affect the outcome of that particular election. Now, there's also a field here called withhold for validation. When I'm doing my forecasting, if I like, I can withhold a certain amount of values at the end of my time series. Withhold meaning don't use those values. For example, I could type in a 12 here, and it would say don't use the last 12 values to either estimate the models or pick the best one. Okay, estimate your model based upon everybody except the last 12. Then what it will do is it'll pretend that it took those models and forecasted the last 12 and give me some statistics on how good it was in forecasting those last 12 observations. Now, when I make the final forecast, I typically won't withhold anything, but in order to validate a particular model, it can be useful to withhold a certain amount and see how good those models would have been in, for example, forecasting the last year's worth of data. Okay? Now, I have a lot to talk about today, so I'm not going to talk about that. I'm simply going to ask it to go ahead and forecast the next 12 observations. Okay? Let's press OK. Now, at this point, it's going to offer to fit for me a number of different types of models, and I'm going to ask it to go ahead and fit everything. In fact, I'll ask it to try random walks, trend models, exponential smoothers, and also ARIMA models. And the ARIMA models, as I'll talk about in a few minutes, have AR terms, they have MA terms, they have differencing, and I will specify here the maximum order, the most complicated ARIMA model that I want it to fit. Okay? And what it's going to do, it's going to go through all of these models and automatically pick one. At the same time, on the right-hand side of the screen, I need to tell it what criteria to use to pick a model. Now, there are a number of different criteria you can choose. The one that's chosen by default, if you don't change it, is Akaike's information criterion. Now, I thought it was useful to actually create a slide all about the Akaike information criteria. What the AIC does is basically minimize the root mean squared error, the standard deviation of what are called the one-ahead forecast errors. What does the standard deviation look like in how far off I am in trying to predict what happens at the next time period, t+1, given all the information through time period t. Okay? Plus a penalty based on the number of estimated model parameters. And by definition, the AIC is 2 times the log of the root mean squared error plus 2 times the number of unknown model parameters divided by the number of observations. Now, what this can be thought of is as a trade-off. It's a trade-off between the precision of the model as estimated by the root mean squared error and also the model complexity. In general, the more parameters in a model, the more complicated they are. Now, very complicated models, although they can fit the past, better than simpler models, often are not that great for forecasting the future. And it's very easy to over-model the past and end up with what becomes a biased model for what happens in the future. The nice thing about the Akaike information criteria, it does a trade-off between the root mean squared error, which is basically giving me a maximum likelihood fit, with a penalty for the number of parameters. And the more complicated the model, the more it's penalized. Okay, so you don't necessarily get the model with the smallest mean squared error. If it's too complicated, it'll fit a simpler model instead. Okay. Well, let's go ahead and do this. Let's go back to Statgraphics and let it go by pressing OK. And then what it'll do is it'll give us a number of things. It'll give us an analysis summary. It'll give us a forecast plot. And those are the two things I'd really like to see. So let's press OK. Now this will take a little while. It didn't take too long, but it actually went through and fit a lot of different models. What it came up with, you can see over here under the forecast summary, is an ARIMA 211 by 212 model. Now, for those of you who stick around for the second half of this talk, which is going to be a little bit more mathematical than the first half, I will define exactly what that ARIMA model is. But it's a rather complicated ARIMA model. It has autoregressive terms. It has moving average terms. It has seasonal autoregressive terms, seasonal moving average terms. And what it results in, and this is the important thing, it results in the following forecast function. What the forecast plot shows me here is it shows me the last observation. That was the 8.2 unadjusted employment rate in November of this year. The center line is the forecast, and it forecasts a slight drop in December, an increase in January, and then a general drop over the next 12 months. Now, that is the forecast function. That's the best guess. You also see, though, around those best guesses, 95% prediction limits. The 95% prediction limits tell me where I am 95% confident the actual value is likely to fall. And you can see that although it predicts in December that things will be a little lower, they could easily be a little higher, at least within the 95% confidence limits. Unemployment is not an easy thing to predict. And that uncertainty is automatically, if you like, built into those 95% limits. And you can see, although the forecasts are down, it is possible that things might go up. Okay, now that's a forecast plot for the unadjusted rates. If I go back to the data input dialog box, I could also forecast the adjusted rates. If I do that, I'm going to want to get rid of the 12 for seasonality, however, and just let it use the non-seasonal models. And there's the forecast for the adjusted, the seasonally adjusted unemployment rates. It's a simpler model. It's just an ARIMA 111 model. And the general forecasts are down. Now, is that what's going to happen? It actually forecasts that by this time next year, we might be down to around 7.9% from the current 8.6%. But notice the 95% limits are everywhere from about 5.5 to about 10. So although projecting what has happened in the past suggests it will go down over the next year, it certainly is within the realm of possibility that it will go up instead of down. Okay. That is, however, the best that could be done given that particular data. Okay. Well, that's all I want to do with that data for a moment. So let me go to File New and clear all this off. Go back to an empty data sheet. And let me pull up a second data file, which I think is also of interest. At least it's interesting to me, and that's a file called stock data. What stock data does is contain the closing prices of a number of different stocks on the U.S. stock exchanges. This is actually daily data. It's starting in January 4th. That was the first trading day in January in 2010, and goes all the way down, I believe, till last Friday. Okay, last Friday, 12/2. Right. Now, the data set I'm going to try these forecasting procedures with, let me go back to my PowerPoint slides, is going to be Apple. Apple stock is an interesting stock, a stock that's actually done quite well over the last year or so. In fact, if you look at the data in my data file, Apple had a low value of $192.05 back on February 4th of last year. It hit a high of $422.24 on October 18th of this year. Would have been a very nice stock to have invested in at the beginning of 2010. You would have more than doubled your money. It closed, incidentally, last Friday at 389.7, so it slipped a little bit from its high, although it's still quite good compared to what it was at the beginning of 2010. Incidentally, the data that I pulled here, it comes from Yahoo Finance. If you're interested in stock price data, yahoofinance.com is a good place to go and get historical data. Now, what I thought I would do is what a lot of people like to do, and that is take this column of data, Apple, and see if I can forecast it. So I'm going to go to Forecast Automatic Model Selection, tell it I want to forecast AAPL, which is the ticker symbol for Apple, and ask it to forecast the data by date. Okay? And I might as well have it go and try all the different models. Now, winner's exponential smoothing is only available if you have seasonal data, but I'll tell it everything else. Press OK. And again, I'm going to ask for the forecast plot and the analysis summary and see what it comes up with. This always seems to happen when I try to forecast stock prices. Of all those models that I gave it to try, it said the best model you can find is a random walk. Now, a random walk model says that basically all of the historical data is completely irrelevant in predicting the future. If a time series follows a random walk, then my best forecast for tomorrow's closing price is today's closing price. And you'll find if you try, and I've tried lots of stocks, that very often they come up with a random walk model. Of all those fancy models we have, none is particularly useful in forecasting the price of Apple stock. Okay. Now, in a few moments, what I'm going to do is see if I can't find a leading indicator for Apple. I mean, maybe there are other stocks that move before Apple that can provide me a leading indicator, but simply trying to project, to do an auto projection of Apple stock is really not very useful. You end up with, when you try this, and I have a slide, is basically a random walk. And what the random walk model implies is the differences between consecutive closing prices are random. That if you look at the change of one day from the day before, I sometimes might call that delta of t. It's called a first backward difference, is that those differences are random. Past history is completely irrelevant. Okay. Now, in order, though, to introduce other variables into my model, I need to start giving you a little bit more theory. And I'm going to go for, actually, for those of you who are interested, probably for another half hour or so. This half hour, though, is going to be a little bit more technical. I really want to talk in some detail now about statistical time series models. And I'll actually show you a few formulas for the models, particularly the ARIMA models, that tend to be quite useful in modeling economic and other types of data. So if you bear with me for a few minutes, I have a little theory I need to talk about. I'm going to start by telling you that time series, when we build a statistical model for them, usually are thought of as consisting of a deterministic component and a stochastic component. The deterministic component is usually called eta sub t, the stochastic component epsilon sub t. Deterministic means it's something not affected by random chance, whereas the stochastic component, the epsilons, are in some fashion affected by randomly by what happens. Okay. Now, as far as the deterministic component, when I fit a time series model, I can use a number of different types of deterministic components. A lot of times I'll assume that the deterministic component is simply a constant mean, that my time series basically varies around some constant value. And if, in fact, the model were what's called stationary, that would imply that it had a constant mean. On the other hand, it may vary around some sort of a trend line, and I've written here a fairly simple linear trend, a plus b times t, as a possible deterministic component. If I was modeling a physical process or some other process, I might also like to include a cyclical effect. For example, I've written down here a sine wave at a particular frequency with a particular amplitude in a phase. Okay, so if you were modeling the variation of something that varied on the cyclical basis, you might like to include some sines or cosines. If you had other input variables, and this is what's going to be interesting in terms of introducing other stocks that might help me predict Apple, you might like to introduce one or more input variables. And I've written a typical linear model in the mx plus b format here, but I've specifically, in this particular model, allowed for the fact that the input might lead or lag the output by a certain amount k. And what I would hope for if I was trying to improve my forecast of Apple stock is that I could find some other stock that moved, for example, k days before Apple. And then I might like to add into my time series some multiple of some other stock at a previous time period. And of course, we can get more complicated. We can add combinations of the different deterministic components if we like. As far as the stochastic component is concerned, the stochastic component is usually considered to be a linear combination of random shocks that affect my variable, my time series, at the present and also in the past. And Box and Jenkins first introduced the notation that I'm showing here, where the stochastic component at time t is represented as a linear combination of a sub t's. A sub t's are random shocks. This is a linear combination of random shocks that have hit me at time t, t minus 1, t minus 2, t minus 3, and so forth. So if you think about the time series or the process that you're trying to model as a dynamic system, this dynamic system has a deterministic component and a stochastic component. And basically, this process, this system is being shocked continually over time. And what you observe at time t is some function of everything that has come before. Okay. Now, This is a very complicated model. Obviously, it says that in general, what happens at time t is a function of everything that's happened back into the infinite past. Obviously, when you're trying to forecast the future, not all of the past is relevant. The recent past may be relevant, but the far past is probably not. Because of this, Box and Jenkins came up with what they called ARIMA models. ARIMA models were designed to capture the stochastics in a parametric way, a simple way that could then be fit to the past behavior of a time series. I have written on this screen a number of different types of models. A very popular type of model for fitting time series, parametric time series, parametric models, is something called the autoregressive model. The autoregressive model, for example, an ARP model, that would be an autoregressive model of order P, expresses the observation at time t as being equal to a mean plus some linear combination of deviations of that time series from the mean at the previous time period, 2 time periods back, and if it were order P, there'd be P terms. It's called autoregressive because you're basically regressing the data on previous values of itself. Okay? So y sub t is a function of what that time series itself did back P time periods. In this case, P is 2. It's a second order model that I've written, but they can get more complicated. Another form of model that's frequently used is something called a moving average model. A moving average model expresses the data at time t as being equal to a mean plus the shock that hit the system at time t minus some combinations of the shock that hit 1 time period before and 2 time periods before. Now you can also come up with mixed models. A mixed ARMA model, well, AR models are normally thought of as order P, MA models as order Q. You can also combine MA terms and AR terms, like PAR terms and QMA terms, and come up with an ARMA PQ model. I've written an ARMA 1-1 model here for you, which says that y sub t is equal to a mean plus some multiple of the deviation of the time series from its mean 1 time period back, plus a random shock at time t, plus some combination of the random shock at t minus 1. That's an ARMA 1-1 model. Okay. And then there's one last class of models, ARIMA models, where instead of applying the AR and MA terms to the data, you apply it to differences of the data. For example, I've written here what's called an ARIMA 1-1-1 model, which incidentally was the model that was picked for the seasonally adjusted unemployment rates. It says that the difference between what happens today and yesterday, or this month and last month in the case of the unemployment rates, is a function of what the change that I observed 1 month back from 2 months back, plus a shock that hit the system at time t, plus the shock that hit the system at time t minus 1. That's actually the mathematical model that the automatic forecasting procedure picked for the adjusted unemployment rates. Okay, now, how do I tell in general what type of model to use? Well, there are a number of tools that Statgraphics provides in its Descriptive Methods section. And actually, the last procedure I'm going to talk about in Statgraphics is the Descriptive Methods procedure. One of the tools that Descriptive Methods provides for me is something called the autocorrelation function. The autocorrelation function plots the correlation between observations in a time series separated by various lags. For example, the autocorrelation at lag K would be the correlation between observations K time periods apart. Now, the interesting thing about the autocorrelations is that if your data follow an autoregressive model, you'll see exponential decay when you look at the autocorrelation function. On the other hand, if you have a moving average model, you'll see a couple spikes at low lags, and that'll be it. On the other hand, if you need to difference the data, a sign of needing to difference the data, which is a sign of what's called non-stationarity, is a failure of the autocorrelation functions to decay. Now, let me go back to Statgraphics if I can, and let me pull up that unemployment rate data one more time. Let's see, data files, unemployment rate, there it is. And let me go and calculate for you the autocorrelation function for the adjusted unemployment rate. Okay. I would do that by going to the Describe menu to describe time series descriptive methods. Now, this runs just like everything else. I pick a time series, I put in the time indices, and I press OK. I can do various transformations. I'm just going to leave it the way it is. I can calculate various output. What I'm going to calculate here is the autocorrelation function. Okay. Here you see the estimated autocorrelation function for my monthly unemployment data. And the way you read this is as follows. You look at the first bar. It has a correlation, a height of the bar of about 0.98, something like that. It says that there is a high correlation between observations 1 month apart. Okay, if the employment rate is high this month, it'll be high next month. Well, there's a high correlation between observations 2 months apart as well, 3 months apart, 4 months apart, 5 months apart, and you see a relatively slow decay in those coefficients. Now, that's because the unemployment data is non-stationary. There is no fixed mean. At least I don't believe there's a long-term fixed unemployment rate. It's low some high, it's high sometimes. And the autocorrelations just don't decay very rapidly. Now, Box and Jenkins suggested if you have data like that, the first thing you should do is difference it. And if I press the right mouse button and go to Analysis Options, I will see a Adjustment Options dialog box that will allow me to difference the data. If I tell it I want one order of non-seasonal differencing, it'll calculate the deltas, the same deltas that I showed you for the stock prices. It'll just take each unemployment rate and subtract the unemployment rate 1 month before. And if I do that, you can see that now the autocorrelations have quite a different behavior. And in fact, there is somewhat of a decay here that would be characteristic of an autocorrelation, an autoregressive model. Although it doesn't have a real nice exponential shape, it's also sort of flat. Even when you look at the differences, the autocorrelations persist lag 1, lag 2, lag 3, all the way out through lag 5, lag 7. Incidentally, on this autocorrelation function, the height of the bar represents the estimated correlation. The red lines are 95% probability limits around 0. Any spike outside of these red limits, which they're around 0, is statistically significant at the 95% level. Okay, so we're seeing sort of autoregressive behavior in the first differences. Now, one of the other tools that Statgraphics provides in the descriptive methods procedure is something called the partial autocorrelation function. The partial autocorrelation function is used to determine what order of autoregressive model would be necessary to describe a time series, or to describe, in this case, the differences. And it's just the reverse of the autocorrelations. In a partial, autoregressive models will show spikes at low lags, while moving average models will show exponential decay. Okay, so if I go back here, press the Tables and Graphs button, I can show you the partial autocorrelations instead. And if I do that, here are the partial autocorrelations with their 95% limits. And basically what you would do is you would look here and you would see, aha, there are definitely 1, 2 spikes in the partial autocorrelations. That would suggest if I use an autoregressive model, I'd use at least order 2. Although there's also a peak out here at lag 5. Now, what we're seeing here is actually the need for a mixed model. And you may remember that automatic forecasting came up with a ARIMA 1-1-1 model. Okay, that's because it's not purely autoregressive or purely moving average. Some combination is actually necessary. Now, when Box and Jenkins first developed these models, these autocorrelations and partial autocorrelations were crucial because you needed to pick the type of model you wanted to fit to the data before you went ahead and fit it. That was before the days of everybody having software which could fit all the possible models and tell you what's the best. But it's still useful in terms of suggesting what types of models are possible. Okay, now those are 2 important tools in the descriptive methods section. And incidentally, I have actually come up with a slide that I've added to the notes here for what the model was for the unemployment rate, the seasonally adjusted unemployment rates. As I said, it was an ARIMA 1-1-1 model. And I've now written it as estimated by the program. It estimates that the change from one month to the next in the unemployment rate equals 0.925 times the change in the preceding month. Okay, so if it went up month to month last month, it's likely to go up almost as much this month. Plus a random shock at time t minus a little bit of the random shock that hit at time t minus 1. Okay? And incidentally, as part of that, okay, as part of the model, you also get an estimate of the standard deviation of those shocks. You should think about the standard deviation of those shocks as consisting of random samples, typically from a normal distribution. A normal distribution with a mean of 0 and some standard deviation. Well, as part of fitting the model, you get an estimate of the standard deviation of those random shocks, which in this case was 0.116. So that is actually the model that was fit by the automatic forecasting procedure. Now, you'll notice that this doesn't contain anything having to do with seasonality. This is all the seasonally adjusted data. If you're working with data that does have seasonality, there's one other tool that's quite useful, and that is something called a periodogram. A periodogram is used to help determine whether or not there are periodic components in your data at particular frequencies. Now, it's well known, at least by people that work with time series, that you can, using something called a Fourier transform, express a time series as a combination of sines and cosines at different frequencies. Okay? In fact, there are a set of frequencies called the Fourier frequencies, which I've written over here as f sub I, which equal 1 over n, 2 over n, 3 over n, 4 over n, and so forth. N is the number of observations in the time series. You can mathematically re-express your time series in what's called the frequency domain by fitting a model of this sort, where you express the observation at time t as equal to possibly a constant a naught plus a linear combination of sines and cosines at the frequencies 1 over n, 2 over n, 3 over n, all the way up basically to n minus 2, n over 2, to 0.5. The highest Fourier frequency is 0.5. Statgraphics will compute for you something called the periodogram. The periodogram takes and plots at a particular frequency the sum of the amplitudes of the sines and cosines at the Fourier frequency multiplied by n over 2. The reason it does that is to scale it up so that if you add up the periodic components, it'll be equal to the corrected sum of squares in an analysis of variance. Now, that's a lot of mathematics. What I like to think about it is, and you can see the way I wrote it on the screen, it's simply an analysis of variance across a set of frequencies. Now, this is actually quite interesting if you apply it to the unemployment data, but we don't want to apply it to the adjusted data. We want to apply it to the unadjusted data. So I'm going to go back to my menu here and go to Describe, Time Series, Descriptive Methods. But this time I'm going to pick the unadjusted time series and analyze it. It won't do any transformations. This time, though, I will compute something called the periodogram. Now, at this point, I've computed a periodogram on the unadjusted time series. Unfortunately, the unadjusted time series is rather trendy. Remember, it was low at the beginning and it was high at the end. And what you're seeing is just one spike here in the periodogram at a very low frequency. Okay, that's the trend in the data. Not very interesting. On the other hand, if I press the right mouse button, go to Analysis Options, and difference it once, and recalculate the periodogram, you now see something quite interesting. You see a set of spikes in the periodogram at particular frequencies. Where these spikes are, incidentally, is they're close to 1 cycle every 12 months, 2 over 12, 3 over 12, 4 over 12, 5 over 12, 6 over 12. For monthly data, if there's a strong seasonal component, the fundamental frequency is 1 over 12, 1 cycle every 12 months. These other spikes here are the harmonics of that fundamental frequency. 2 over 12, 3 over 12, 4 over 12, 5 over 12, 6 over 12. Now, were the cycle and unemployment rate over the year a pure sine wave, you'd only see a spike at the fundamental frequency. But if it's not a sine wave, if it's a square wave, for example, you'll see lots of power at the harmonics as well, but as potentially at the fundamental frequency. Now, you'll also see a little bleeding in this case from the harmonics and the fundamental frequency down to the nearby points. That's coming because my data set is not, the length of my data set is not a multiple of 12. Okay, had I a nice, had the value for December of 2011 such that n were a multiple of 12, then the Fourier frequencies would be nice and clean, and you wouldn't see this leakage around the frequencies. Where the periodogram becomes really useful is when you're searching for unknown cyclical effects. Okay, I know that unemployment rate is cyclical with a period of 12. But there are other times when you're exploring data where you're not sure whether or not there is power at some particular frequency. And the periodogram is used as a descriptive tool to help us locate and identify periodic effects that we might not know about. I'm demonstrating it here just to show you how it works, but in general, it's more useful if I don't know what cycles might exist, because it can tell me what sort of periodic effects might exist in my time series. Okay, so that's quite a useful tool if you're dealing with data that might have periodic effects. Now, one last tool that's important, and now I'm going to get back to my stock price data, is the cross-correlation function. A cross-correlation function plots the linear correlation not between observations of a time series in itself, but between observations of a time series, one time series, and another time series. Okay? I'm going to take my stock price data here in just a moment and actually compute cross correlations, because I would like to know whether or not there's another stock that moves before my Apple stock. Now, we will define a cross correlation, incidentally, at lag k as the correlation between the output time series that I'm trying to measure at time t and an input time series x at time t minus k. I'm hoping I can find another stock that shows a significant correlation at perhaps a lag of 1 or 2 or 3. 1 day before, 2 days before, 3 days before, something like that. If I can, then I can add it to my model and potentially get better forecasts for my Apple stock. Well, something other than a random walk. So a cross-correlation function is quite useful if you're trying to find a correlation between two different time series. And I'm hoping here I can find a leading indicator for my Apple stock. All right, so let's go back to Statgraphics. Let's put away our unemployment rates, okay, and pull back up our stock price data. Time, data files, stock data. There it is. And the way I'm going to start is I'm going to start by going in here to describe time series descriptive methods again. This time, however, what I'm going to do is I'm going to start by putting in my Apple stock and versus date and press OK. Okay. Now, if I take the defaults, well, I won't take the defaults because what I want, well, I'm going to show you first the autocorrelation function and second the cross-correlation function. Okay. The autocorrelation function for Apple stock is similar to what you saw for the unemployment data. It's failing to decay because the data is non-stationary. If I right-click, go to Analysis Options, and take the first differences, press OK, you'll see that the first differences are fairly random. Now, I do notice actually a little bit of a spike here at like 7. That would imply that changes in stock price and Apple stock are correlated with what happened 7 days before. Now, you shouldn't get too excited about that sort of thing, though, because what you have around here, around these spikes, are 95% limits. 95% limits, incidentally, are violated 1 time out of 20 just by chance. I plotted 24, so I actually could expect at least one of my spikes to violate the 95% limits, at least a little bit. Anyway, it's pretty clean. We saw before that Apple is pretty much a random walk. The differences from day to day are pretty random. What I'm interested in doing, though, is now seeing if there's a cross-correlation with another time series. Now, if you go down here to this pane, this is where the cross-correlation is normally plotted. It says no input time series variable specified. Well, I can remedy that. I'll right-click, go to Pane Options, and now pick a different stock. And of course, the first thing I tried when I was playing this weekend is I tried Microsoft. I wonder if the price of Apple stock is correlated with the price of Microsoft stock. Now, you'll see that this box down here is checked. It says Apply Adjustments to Second Time Series. Since I've already differenced Apple, it's also going to difference the Microsoft stock. And it'll actually show me the correlations between changes in Apple stock and changes in Microsoft stock, which is normally what you would want to do. Let's press OK, and here we go. Here is the autocorrelation function between Apple changes in the Apple stock price from the previous day and changes in the Microsoft stock price the previous day. And in fact, there is a strong cross-correlation at lag 0. If Apple went up today, Microsoft probably went up today. If Apple went down today, Microsoft probably went down. That may be interesting, but that's not helpful. It doesn't help me forecast what's going to happen tomorrow. What I'm hoping for, actually, is that I see significant spikes at these positive lags here. These positive lags, lag 1, lag 2, lag 3, lag 4, lag 5, would correspond to a correlation between Apple stock today and Microsoft stock changes in the past. Well, there's nothing of any interest here. Okay, Microsoft is not a leading indicator for Apple. Well, if Microsoft doesn't work, maybe one of my other stocks will work. And in fact, I picked a bunch of other stocks to try. IBM, Cisco, Intel, Dell, Yahoo, eBay. Then I tried the Dow Jones, the Standard & Poor's Index, the NASDAQ. Gave me the same thing. There was no significant cross-correlations. So I said, well, let's start picking some other things. So for fun, I picked AT&T, Anheuser-Busch, Coors, and Boston Brewing, who makes Sam Adams. And I actually did find one stock that has a significant correlation with Apple, and that's Bud. There appears to be a significant correlation between what happens to Apple stock today and what happens to Bud. Anheuser-Busch makes Budweiser, by the way. What happens to Bud tomorrow? Now, actually, I was hoping that I'd see significant cross-correlations at positive lags. Okay, these correlations out here would mean that Bud was a leading indicator for Apple. It's not. It's on the other side. Actually, Apple leads Anheuser-Busch. So what happens to Apple today is negatively correlated with what happens to Anheuser-Busch tomorrow. Well, that's not helpful in forecasting Apple, but it is helpful in forecasting Anheuser-Busch. If I wanted to forecast Budweiser, Anheuser-Busch, I could use Apple as a leading indicator for Anheuser-Busch. Now, to show you this correlation, let me just do a quick scatter plot. Let me push the XY scatter plot button here. And let me do a scatter plot for you so you can see the relationship. And the scatter plot I'm going to do for you is I'm going to put differences in Bud. And now I'm going to use on my XY data input dialog an operator called diff. I've typed here diff of bud. That operator will take these differences I've been talking about, and you can use it on any data input dialog box to quickly take the differences, the first differences of a set of data. And I'm going to ask to plot diff of bud versus lag, L-A-G, parens, diff, parens, A-A-P-L, parens, comma 1, parens. This says take the differences of the apple stock, and then lag it by 1. Okay, you can see this in the notes if you download the notes afterward, by the way. You can see these particular operators. But basically I'm saying give me a scatter plot of the changes in Anheuser-Busch on the y-axis and the changes in apple the previous day on the x-axis. Well, what you get is this. You get a scatter plot, and if you have a little bit of an imagination, you can see the negative correlation. Or if you don't have an imagination, I can always go up here and put a robust lowest smooth, for example, on it, on the scatter plot. And you can see that there does appear to be a little bit of a negative correlation. If apple goes up today, Anheuser-Busch will go down tomorrow. Or if apple goes down, Anheuser-Busch will go up. Now, it's a very weak correlation. You're not going to make money off of this correlation. It's actually quite weak, but nonetheless, it is interesting. At least it's the only correlation I could find in my stock prices. Now, having seen this, I can then go ahead and build an input-output model. And my last example of this webinar will be building an input-output model. Building a model that will try to forecast Anheuser-Busch stock prices based upon what happens with the Apple stock the day before. And to do this, what we're going to do is we're going to build a model for Budweiser that includes Apple as a lagged regressor in an ARIMA model. That is, we're going to add to an ARIMA model a term involving changes in Apple stock one time period back, and use that to help us predict what happens to Budweiser. Okay, now how do we do that? Well, there's a couple steps involved. The first step will be going back to my data sheet and forecasting the input time series. If you have a leading indicator, okay, and it's not back far enough in the past, you may actually have to start by forecasting the input time series. So the first thing I'm actually going to do is I'm going to go back to my data set here, to my data sheet. Go to the bottom of my data sheet, and where I see Apple stock, put in some forecasts for what I think is going to happen to Apple in the future. Okay? Now, currently, at least on December 2nd, it was $389.70. Well, we know that Apple is a random walk, so the best forecast for the future is the last price. So I'm going to take that last price and paste it into several cells in the future. Had I a more complicated model for Apple, I'd have to take the forecasts that were generated by my forecasting model for Apple and type them in the data sheet. Okay. Well, I wouldn't actually have to type them. The forecasting procedures will save the forecast to the data sheet if you want them to. I don't have to do that here because it's a random walk model, and my best forecast for Apple is that it's going to be whatever the last price was. Okay? That's step one. Now what I need to do is I need to go set up a forecast model for Anheuser-Busch and put Apple in as a lagged regressor. Now, the way you do that is the following. You go to forecast, and you do it, the easiest way to do it is as a user-specified model. I'm going to tell it now that I want to forecast bud as a function of time. And let's go down here, and where it says number of forecasts, type in 5. I'm only going to forecast the next week for Anheuser-Busch. I then press OK. Now, we know that the best model, well, I haven't shown it to you yet, but the best model for Budweiser is also a random walk. What I want to do is actually take the random walk model and add Apple as a regressor. Now, unfortunately, you may look at the top right here. You'll see that regression, there's a button for regression. See it says regression on the top right? That's where you add the regressors. Unfortunately, you can't add a regressor to a random walk model. You can, though, add a regressor to an ARIMA model. And if I pick the right ARIMA model, it's equivalent to a random walk. In fact, in a ARIMA model with 0 AR terms, 0 MA terms, no constant, and a non-seasonal order of differencing of order 1, it would be called a 0-1-0 model, is equivalent to a random walk. Now you'll see that the regression button over here is lit up. And now I can go over here and type in, as a leading indicator, lag, AAPL, 1, close parens. Okay, which is changes in Apple stock 1 period before. Now, again, you do not have to difference the Apple stock. If you're differencing Budweiser, it'll automatically difference the Apple stock for you, any of the lag regressors. So I'm simply going to type in lag AAPL1, press OK. Press OK again. And now what I'm going to ask for is I'm going to ask for an analysis summary and a forecast plot, and press OK. Now, if you look at the analysis summary, you can see right here that it's added to my mathematical model the lag AAPL at 1. And in fact, it estimates a multiple of the lag differences in Apple stock minus 0.0289. And there's a p-value on it, and you can see that it's actually statistically significant. Any p-value below 0.05 would be statistically significant at the 5% significance level. Okay. Now, if you want to see what that model is, this is what it actually is. The mathematical model says that the price of Anheuser-Busch at time t can be represented as the price of Anheuser-Busch the day before minus 0.0289 times the differences in the Apple price at t-1 and t-2. Now, that's a very small effect. Okay? It is, though, statistically significant, implying that for some reason the changes in the Apple stock price tend to lead changes in Anheuser-Busch. Now, you can see that it's not very significant because if I show you the forecast function, you have to look, and I don't know how good your screens are, but you have to look really hard to see that this line is not completely horizontal. Now, the reason that is, incidentally, is that Apple didn't change much between the 1st and 2nd of December. For fun, let's suppose, though, on the 2nd of December, Apple stock tanked. All of a sudden, Apple stock went down a lot. Let's say it went down to 350 on the 2nd of December. If I then look at the forecast functions, Now you can see actually a big change in Apple would affect a corresponding change of the opposite nature in Anheuser-Busch. Not big enough, incidentally, that the 95% limits wouldn't allow for down or up. But for some reason, and I don't know what it is, there does appear to be some correlation between the price of Apple stock and the price of Anheuser-Busch. Okay, and incidentally, it's not just Anheuser-Busch with Apple, it's Anheuser-Busch with the entire stock market. I can actually use the Dow Jones Industrial Average as a leading indicator for Anheuser-Busch. One can only imagine, you know, if the stock market goes down a lot, people may order a lot more beer. Anyway, it's positive for Anheuser-Busch the next day if the stock market goes down today. Very small, though. Don't go out and bet a lot of money on that. It's a very small effect, but it's actually there. Okay, well, for those of you who are still here, and I notice it's most everybody, if you need more information about what we've talked about, you can go to www.statgraphics.com or send us an email. And the best place is info@statgraphics.com. Okay, now I'm going to try to answer some questions, and we'll see if we have any questions. Yeah, we certainly do have some questions. Incidentally, before I answer the questions, I'm trying to decide on the next webinars to do. A couple that have come to my mind would be sample size determination. There are quite a number of procedures in Statgraphics that can help you decide how much data is necessary to run different statistical procedures. I've also been thinking of doing a seminar on life data analysis, survival times, product reliability. There are a number of procedures in Statgraphics that I have not talked about that are good for that type of data as well. If you have a topic you'd like to hear, send an email to info@statgraphics.com. Let us know what you would find useful. I probably won't do the next webinar until after the first of the year. It's getting really busy around the holidays, but there are quite a number of topics I could talk about. Okay, let's see what sort of questions I've gotten. First question, what can help determine the data set length, rows of data? How many data points do I have to get good time series? Output could be impacted by how many data points I have. Is there a best way to determine this? You know, that's an interesting question, particularly when you're dealing with time series. I remember when I was teaching back at Princeton in the engineering school, there was a postdoc there, name of Darren Shu, who used to talk about the law of large numbers and how it applied to time series analysis. He said in time series, the law of large numbers applies in two different ways. It applies as it normally does when we're analyzing random samples, in that the more data you have, the better off you are, in that the statistics will be more powerful, the estimates will have a smaller standard error, and so forth. He also, though, said the second law of large numbers is that if you sample a time series long enough, something's sure to change, so that any of the simple models we have, or even the more complicated models, which may fit over a medium time range, are not going to fit over a long time range. And therefore, if you take too much data, it can sometimes be detrimental in that you can't find anything that fits the entire history. So it's actually a trade-off between how well my model is going to fit the entire history that I have, as well as the number of observations. Now, the real way to judge is typically to look at the standard errors of your coefficients. Okay, right now the estimate of my coefficient here is about minus 0.03 with a standard error of about 0.01. So a confidence interval on that parameter would be about minus 0.03 plus and minus 2 times 0.01. You know, it's hard to say in general how much data you would need. Rarely am I going to be modeling time series with much fewer than 100 observations. Typically, if you're modeling a seasonal data set, like, for example, the unemployment rate, where you have 12 observations for each season, I've typically heard rules of thumb that you need at least 5 or 6 seasons, 5 or 6 full replicates in order to get any reasonable sort of a model. That's not something I actually have a good answer for, but I'll be happy to actually do a little research on what you need for time series. But the only thing that comes to mind off the top of my head is typically 5 or 6 seasons worth of data. I mean, that's a bare minimum. We'd certainly like more than that. 10 would certainly be considerably better than 5 or 6. So unfortunately, I don't have a real good number on that, but I'll be happy to do some research on that. It also affects, incidentally, when we're doing descriptive methods, it affects the probability limits, for example, on these cross correlations. If I did not have enough data, these probability limits could be quite wide, and my ability to detect significant cross correlations between 2 time series would be hampered if I didn't have enough data. Here you can see the limits are at about plus and minus 0.1, which means I have a pretty good chance of seeing cross correlations up around 0.2, plus or minus 0.2. And they really need to be that big in order to have much significance on the fitted model. So I probably have enough data here. Of course, I have about 435 days worth of data here. 100 observations is typically, at least it feels to me like a sort of a minimum on doing any of these types of models. I'll do some more research on that, though, before the next seminar. Okay, that seems to be the only question that was relayed to us. Well, I know there must be some more questions out there. So if you have other questions, feel happy to send them after you've had a chance to potentially review the notes. And again, I have put up on our website the most recent data sets. Well, we have all the seminars, actually. And as soon as we get a chance, we will post a recording of this particular webinar on the website as well. So if you want the notes from this webinar, you want the data sets, you want to listen to everything again, and I know I did talk a little fast today. There was so much I wanted to talk about. You can go ahead to www.statgraphics.com, click on the link at the home page that refers to the webinar, and you'll see what we've posted. Okay. I hope you found that all helpful. Any comments you have, please send them to us. Otherwise, have a good day, and I'll talk to you next after the first of the year.